Esatto.
Yeah, the ISR was also the place where many experimentalists learned to do collider physics. Our next speaker, who is perhaps better known for his work as as spokesperson of Delphi, and also as a pioneer of hadron therapy, was one of these early students at the ISR. So please welcome Ugo Amaldi. Thank you.
Very much. Thank you for the invitation. 50 years ago, we were studying the first head-on proton-proton collisions. 13 years later, Maurice Jacob divided the life of the ISR in 3 periods: a brilliant start, a somewhat difficult time, and a very active and interesting program. I will follow this trail with 3 opening remarks. First, the ISR was the only CERN collider built without a specific physics goal. Second, the program was shaped by the dominant view at the time. Proton-proton collisions are soft processes. Third, the ISR committee favored the PS approach, many experiments performed by small groups. The dominant view at the time was that particles are created at high energy in soft processes, that is, inelastic collisions, which cover 80% of the total cross-section, produce pions, kaons at small PTs, 0.3 GeV typically, which is complementary to the dimension of the proton colliding, 1 Fermi. The elastic collision, 20% of the total cross-section, are the shadow of this inelastic collision in the sense that the wave is absorbed by a kind of gray disk, and it is diffracted, and this is the forward elastic cross-section, which peaks forward. The momentum transfer Q, which is energy by the angle, is small, and one expects this peak to change with energy. In the first period, 71-74, the major instrument for inelastic collision was the split field magnet. This was an enormous endeavor at the time. Imagine 20 proportional chambers, 70,000 wires, only 5 years after the first tiny chamber built by Sharpak in this laboratory. The idea was by Jack Steinberger. A field was vertical here, vertical on the opposite side, and was 0 at the center, which, as I'll discuss later, has been some inconvenient for the development of the physics program. Hadron-hadron collisions at the time were described in the framework of the so-called Regge theory. In case of electromagnetic force, which is feeble, electron-electron scattering is due to the exchange of a single virtual particle, a photon, as everybody knows. In the case of strong force collisions, this is not possible, but this theory was developed in which the exchange was not a single particle, but collections of particles called having different masses and different spins, which were called a trajectory. So exchange of Regge trajectory was the way in which the phenomena were explained at the time. Elastic scattering between 2 hadrons in this framework is due to the exchange of the same Pomeron trajectory, simply the Pomeron. You see, an hadron or an antihadron against a proton gives a scattering particle. And this theory predicted very formally at the time that for energy going to infinity, the total cross-section will become constant and equal, both for hadrons and antihadrons. This was a very strong prediction. And this, interestingly enough, in July 71, confirmed by the Serpukhov data Prokoshkin group, who published a paper which has the following figure. You see, antiproton, proton, proton-proton seem to converge, pi plus, pi minus, k plus, k minus seems to converge at high energy, and the proton-proton cross-section is really constant here, so much that at that time, a sentence which would have been heard in this auditorium very often is, proton-proton asymptotia is already reached for beam energies of 100 GeV. In the data, as you can see, the k plus going up. But the prejudices were so strong that the authors wrote, this figure suggests that the total cross-section for a gas proton will approach the asymptotic value, which of course exists, from below. This was the status of the knowledge when the ISR was switched on. In intersection region 8, the total cross-section was measured by the Pisa-Stony Brook collaboration with this enormous scintillator detector, a very large detector for the time, which gave a lot of results in correlation between particles that I will not discuss for lack of time. The luminosity, which was needed to get a cross-section from the rate, was measured, as was already quoted, with the method invented by Simon van der Meer, the great Simon van der Meer, mentioned many times already in few speeches here in this auditorium. The two beams of currents I1 and I2 crossing at an angle, as you know, 15 degrees, were moved vertically in small steps, precise steps, and the scan was the rate of any counter surrounding the interaction region. From this, one could get effective height and the luminosity. So this was used by Pisa-Stony group, by the CERN group, home group, everybody else, and is still in use, as has been said already before me. In the intersection region 8, the total cross-section was measured by the CERN-Rome collaboration to the forward elastic cross-section. They used the Roman pots, which are movable parts of the donut, which after the stacking, which has been just described of the beam, were moved close by so that the edges of this odoscope sitting on the bottom of the pots could be put very close to the beam, reaching about 9 millimeters sometimes if the stack was quiet. These Roman pots, many people have asked me why Roman pots, so I must make here a personal remark. At that time, Giorgio Matti and myself were traveling frequently between Rome, where was our laboratory, and CERN to discuss with a draftsman of Franco Bonaudi's support group, who was transforming our rough sketches in precise professional drawings. And once we came and we saw that in a corner of this drawing, the man has written "Le pot de Rome." So the translation of pot de Rome to Roman pots was easy, and it stuck, as you know very well. So this ends my personal reminiscence of that time. And I go on speaking about the result of the CERN group. They got this behavior of the elastic cross-section as a function of Q square. There is the strong interaction part, which is exponential, and then there is the Coulomb interaction due to the two charges of the two protons, which shoots up, and this is the shape measured at the maximum energy we got. In the theory, which is still valid, the S-matrix theory, one writes the amplitude for the cross-section, which is the square, gives the total cross-section as an imaginary part, this I, plus a small real part. Imaginary because in this language, a absorption gives a scattering which is imaginary, and the real part is smaller than 0.1, typically 10%. Two consequences come out. One is the optical theorem, which roughly says the total cross-section is proportional to the forward cross-section, that is this point, red point here. You measure that and you get the total cross-section with the van der Meer luminosity. And the second point is the dispersion relation, which expresses the real part, the fractional real part, I should say, at zero momentum transfer as a function and integral over all energies of the total cross-section. So measuring the real part of the center energy gives you an indication what is the energy behavior at much higher energies of the total cross-section. With the first optical theorem, the two collaboration, the CERN-Rome measured the total cross-section so that the two collaboration, Pisa-Stony group and the CERN-Rome, could publish this graph, which is quite well known. These are the Serpukov data, and this is the 10% increase found in 1973, which proves that asymptopia does not apply to protons, and later on we knew that also doesn't apply to other particles. And the Pomeron is much more complicated than what was foreseen. Nowadays, you still speak about the Pomeron, but you hear about a soft Pomeron, hard Pomeron, double Pomeron, Pomeron cuts, and triple Pomeron vertices. So the theory is still there, but a lot has changed because of this result. In In intersection region 8, the CERN-Rome collaboration later on measured with new Roman pots the real part. You see, these are very accurate measurements of the real part, and applying dispersion relation, as I told you, you can know what happens at high energy. And so this is the graph, which was published by the CERN-Rome group, which shows that the cross-section not only increases up to 60 GeV, but continues to increase up to 300 GeV, and the increase is 47%, about 50%. By nowadays, at LHC, the increase, I just checked yesterday, is 260%. So this is not a small effect, 260%, the small 10% effect found at the ISR. ISR experiments have shown that the proton total cross-section increases by 50% when the collision energy increases from 15 plus 15 GeV to 150 plus 150 GeV. Now I pass to hard physics, starting from the famous and memorable Rochester Conference 72 in Fermilab, where the SLAC group presented new data and analysis of electron deep inelastic scattering, which confirmed that point-like partons exist within protons, and they started to say that partons are probably quarks. Of course, quarks idea was around, but it was the first indication coming out. This was a memorable conference, by the way, for those who are in the field, because in the moment in which our field changed direction, this was the startup of building really confidence in the new standard model. This was a very important moment, just at the startup of the ISR, by the way. Then, and this is also a very famous paper, Don Perkins used old Gargamel data to prove that neutrino scattering, which is the same phenomenon, you see, in deep inelastic scattering you measure electron, in deep neutrino scattering you measure the muon, and the only difference is that here the electromagnetic force, there is exchange of a virtual photon of high energy, which kicks off a quark from a proton. In this case, there is the new language that has been introduced later on, of course. A quark is scattered off from a proton by the exchange of a W. This deep inelastic scattering was really first evidence that partons are quarks. So it was really a changing moment, and this is very important because at the same conference, this is something which is not well known, ISR collaborations announced the discovery of large transfer momentum hadrons. So studying at the same time what was happening in proton-proton collision, 3 experiments, R103, in CERN, Columbia, Rockefeller, lead glasses and counters, Saclay-Strasbourg collaboration, which had a small magnet and Cherenkov counters, and the British Scandinavia collaboration, large magnet, you can see it here, plus Cherenkov counters and rotor chambers, they found independently at the same time that there are large transfer momentum hadrons coming out in this collision. This was, I insist, at the same time when Gargamel was saying that this particle are quarks. This, of course, could not be said in the case of the ISR data. I show you only one picture because it would have been too much to explain all the figures. This is a figure taken by the CERN Columbia Rockefeller collaboration on pi0. They had the glass walls, as I said, gamma-gamma detected, and so one could reconstruct the pi0, and you see that the pi0 spectrum at 52 GeV is orders of magnitude higher than the soft behavior expected when we started, the one that I said limited by 0.3 GeV momentum. So that was a big discovery, and this is a very important moment. And of course, immediately, everybody understood it. This was the interpretation. A parton, we could not say a quark at the time, would collide with another parton, and the strong force, in this case strong force, not electromagnetic, not weak force, would produce 2 partons and parton jets, and the PT hadron would be one of the decay of one of these partons. And so experiments have shown that partons behave as point-like objects also when they interact through the strong force. Of course, next would have been the moment to detect jet, and there the problem started, the new period that was announced by Maurice at the end of running of the ISR came in. But there was another thing happening before, which to me is even more serious, if I may say so, because we all felt a lot of frustration in September '74 when the J-psi discovery was announced, as you know very well, by Sam Ting and Burton Richter. Because experiment 103, the CERN Columbia-Rockefeller collaboration, had these two very big wall of glass Cherenkov counters. They could detect photons and also electrons. And they were looking for pair of electrons. In fact, the experiment was done also for that, to see whether there are peaks in the plus-minus cross-section. But the two-arm trigger was dominated by the photons coming from the pi-0 decay. And so, to write on tape less than 10 events per second, cuts were set above 1.5 GeV, thus excluding the possibility of seeing the 3.1 GeV peak that was the J-psi. This is something that the people are expert. I know it very well because I was the ISR coordinator in '75, so I've been living to these states and all the meeting and discussion of this time. It was very sad. Luigi Di Lella said in one seminar, and our discovery prevented a more important discovery. The discovery of large PT pi-zeros prevented the discovery of J-psi. Would have changed, to me, the history of physics. In part, also would say, this meeting would say that ISR was a great machine because here, and I would not be speaking here because so physics would have been completely forgotten, by the way. J-psi, this was shown, a picture by the same group, just a few months later than the announcement. Now, this was a bad start of a bad period, a somewhat difficult time, no instrument to trigger on jets and to study them, and ISRC was very hesitant in approving large coverage magnetic detectors. In '76, organized the ISRC working group to evaluate solenoid versus toroidal solution for the magnet to be built. And the results were important, seminal even, I would say, for the axial field spectrometer, I will show in a moment, and for even the detectors of the future proton-antiproton collider. So from a bad, always you get a good, but a bit late. I show you the two big detectors, which eventually were very active, producing very active and interesting physics. Superconducting solenoid by the CERN Columbia, now Oxford Rockefeller collaboration with cylindrical dish chambers and two arrays of glass Cherenkov counters. You see, this was an extension of the two arrays I was mentioning before of glass Cherenkov counters. And the axial field, open, one would say, axial field spectrometer with Helmholtz coil, a very open magnet, which had fantastic detector, liquid argon calorimeter, imagine at the time, and uranium scintillator hadron calorimeter, a big collaboration, and this was for me eventually the evidence for jet production. I will quote only one important discovery of this period, which is single photons at large PT. This was obtained by three collaborations with various experiments. I list them here. At the function of PT, it was found that there are single photon producers. Not an easy task to find single photon in all this background of photons coming from pi-0 decay. And this was an early experimental indication of the validity of QCD. So you see, there was quite a lot of results which gave contribution to the understanding of the... but there was a lack of general recognition of the importance of the ISR hard physics, unfortunately, around in the physics world, has already been mentioned by. And this some reasons which I'll try to explain. But before, let me tell you that no time to speak of observation of sharp hadrons, studies of Drell-Yan process, and experiments on the emergence of jet structure. This I have to leave out. My last transparency. 10 years ago, we had the anniversary, first anniversary of the first proton collisions, and we had a symposium, and a yellow report has been published. And Pierre Dariula wrote in this yellow report these two sentences, with which I want to finish. We, who work at the ISR, tend not to attach much importance to this lack of recognition because for us, the main legacy has been to have taught us how to make optimal use of the proton-antiproton collider. We tend to see the ISR and the proton-antiproton colliders, both at CERN and at the Tevatron, as a lineage, father and sons, the success of the latter be indissociable from the achievements of the former. And I share this point of view. And I think this is just the right time to pass the microphone to the best of the ISR sons. Thank you.
Thank you very much, Ugo. We have time for a quick question. You have your microphone.
Yeah, Ugo, beautiful talk. You said at the beginning the machine was built without physics motivation. But in fact, as many of us remember, in early 1964, the idea of quarks were discovered. In May 1964, I was an undergraduate, I heard a lecture in Oxford by Vicky Weisskopf, the DG, and he was saying we really must build the ISR to discover quarks. So there was a motivation. I'd like to make one other remark. Of course, the large PT was very important, but there's a soft contribution which I think gets overlooked. Before the ISR, we didn't know there was a central rapidity plateau. Most people thought there was, but I was at SLAC at the time, and I remember Dave Ritson, an old cosmic ray physicist, saying, you people who think there's a central rapidity plateau, it's all nonsense. We know from cosmic ray physics there are going to be two fireballs going forward and backwards. So actually, the basic structure of high-energy events was discovered at the ISR, but it's now considered so obvious that you don't get the credit for it.
Thank you very much for this interesting comment.